First of all, a bit of an apology. I know I said that I would try and get you the assignment brief Friday afternoon, and then I came down with a stomach bug on Friday and was basically out all weekend. So I will do my damnedest to get it to you guys by 5 p.m. today. You still have plenty of time to do it. You have like until the end of term, and realistically it's the sort of thing which should probably be knocked out in a few days. But it's more just making sure you guys have plenty of time to think about things and explore the parts that you want to do. So as I said, it'll be all about all this low fidelity prototyping under the guise of a like brainstorming and very early stages of prototyping what you would like to, like your ideal virtual reality training simulation. So this will all be covered in the handout, but it'll be things like, you know, maybe look at some different applications where VR training has been used, pick one of those, or perhaps pick something else that you think it would be applicable for. You know, do a little bit of a look into what things would be important. What if you were designing it, what would you think would be important, and then run through some of the low fidelity prototyping exercises we've looked at. So it might be doing some sketches, and you know, you guys can come together as a group and show your sketches to each other, brainstorm together. You'll still be required to submit your own report at the end of it, but you know, you're certainly welcome to work as a group on the brainstorming exercises. And even if you want to do some role playing, you know, get somebody else to role play as you're doing your virtual reality medical training thing. Get someone to lie on the table while you wave a cardboard box over them and pretend it's some VR controller or whatever. But yeah, I'll get that out, and then on Thursday, at the start of class, we can have a bit of a discussion if there's any questions. And obviously, if there's any questions before then, you guys can come and talk to me or flick me an email. And you know, if it's something that I feel I haven't explained very well, I can put something on Learn, or send an email out to all you guys with anonymized. So don't worry, I won't be like, oh, this person asked this really dumb question. It'll be more like, okay, I obviously haven't done a good job explaining it. So. So everyone happy with that? No questions at this point in time? No? Cool. We may be getting a couple more. As I mentioned, there's another course that I'm teaching that a few people were thinking about maybe dropping in here, but I did tell them there was a lecture on today at 10 and they're not here, so perhaps I've changed their mind. But today we're just going to finish off what was left of the low fidelity stuff, and then we're going to start moving into the software side of things, so programming and all that stuff. So you guys are happy with sort of what we've covered here? I know it's been pretty vague and you know, just sort of touching on it again. A lot of that's been shifted over to the design parts now, so you go into it more, and the assignment marking will reflect that as well. It's not like this is going to be worth 50% of your grade. I can't remember the exact amount I gave, but I think it's worth about half of what the other assignments are worth. So it sort of reflects the amount of time we spend on it will reflect the grading of it. All right, so we were wrapping up role-playing Wizard of Oz studies last week, and we just sort of ran a bit out of time, so we looked at a few examples, talked about why they do it. I think the last thing we talked about was this IBM text-to-speech and how you know, IBM potentially saved themselves millions of dollars and thousands of hours of time developing this thing by doing a simple Wizard of Oz study, which showed that people who actually thought they'd really like to use text-to-speech would not actually like to use it because it was really tiring and exhausting. So there was one other example that I thought sort of illustrates this point quite well, sorry. And that's this study which came out in 2012, where some guys were doing something around mobile navigation. So this is navigation for blind people. Obviously, they can't just pull out their phone and look at their GPS or whatever. So they were looking at an auditory interface. You can see this guy's blindfolded. He's got a cane to make sure he doesn't trip over anything. And he's got a pair of headphones on, which are providing him with guidance instructions. So you can imagine there's obviously, this is something you have to be careful with. Blind people are already at a disadvantage in that they can't see any potential hazards. And then if you are trialing out new stuff on them, you don't want to overwhelm them, like we saw with the examples of the people with the in-car assistant, and the guy had completely forgotten that he was supposed to be driving a car anymore and was sort of just holding the steering wheel like that. So you don't want to be feeding them too much data, have them completely overwhelmed and then walking out to traffic. So again, in this case, what they were doing is they were basically Wizard of Ozing the whole thing. So as far as this person is aware, they are walking along and they have some computer which is somehow magically giving them instructions and telling them how to get around or follow through this city. They have, chances are they knew that they had someone with them to make sure that they didn't hurt themselves, but what they didn't realize is that there's actually another person there who's basically controlling the system and is pushing buttons, which is effectively relaying the audio through Bluetooth or whatever from this device. So by doing this, they could made things a lot safer than actually building the system and testing it out. We had a PhD student here a long time ago who was working with auditory interfaces, and that was for, she was doing more sort of menu navigation, stuff like that. So if you're doing a task where you can't take your eyes off it, how do you allow people to navigate through data sets? And she was working around, you know, having audio menus. So how do you do an audio menu? You can obviously just repeat file, edit, view, tools, whatever, but that it's quite slow, particularly when you become an expert user and you know exactly, you know, I need to get to the fourth one and I have to wait till it gets all the way there. So she was experiencing with like spatial audio, so how much mental processing are people able to deal with if I hear at the same time all the tool options, but they're coming from 15 degrees around me. So file is here, edit's here, blah, 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 and then I can just sort of point in a direction, because once you get skilled at that, it's actually not so bad to figure out, to hear everything at once. And you know, I'm just looking for the tools menu, so you're able to filter out tools from the other 5 words which are set at once and just sort of pinpoint, okay, that came from that direction, so I want to activate that menu. So even in that, as a new user to it, it was pretty overwhelming. Like I had to sit there with my eyes closed, like trying to really focus on what I was doing. So being able to have, you know, this sort of situation where you can mock the whole thing up, you can obviously Wizard of Oz, as we talked about with some of the other examples, you can change them on the fly. So if things aren't working as well as you expect, you don't have to just can the whole experiment. You can, because it's a human, you can be like, this person, you know, perhaps the English is a second language and they don't, you're saying, you know, head west, or they're not even English as a second language, they're new to the city, and you're saying head west, head right, head west, head east, and they're terrible with directions, you might instead choose to change that to turn left, turn right, because that's something that hopefully most people are familiar with, their left side and their right side, whereas east, west, north, south perhaps not so much. So by doing this, you can ensure safety, you can react a lot quicker, you can change things on the fly depending on how it needs, and again, they didn't have to build this whole system. So being able to, you know, GPS these days is pretty good, but even 10 years ago, the accuracy was down to, you know, maybe a few meters, and that could be the difference between me standing on the sidewalk and me standing in the middle of the road. So having to build a system which makes sure that people are going to stop at the sidewalk and tell them to turn left and right, and not tell them to walk out to the middle of the road and then turn left and right, is something that possibly is just, we're not ready to trust technology with. So there's lots of motivations for running things with Wizard of Oz beyond the fact that it actually means you don't have to build anything. Or in this case, you know, you just build a website, or an app or a website with a bunch of buttons, and when you push it, it says turn left, turn right, whatever. So really super simple application which allows you to test some quite complex problems before actually building anything. And there's a reference to the paper if you're interested in reading a bit more about that. Cool, so does anyone have any questions about the role-playing or Wizard of Ozing stuff? No? So it is, again, it's quite intuitive, but they are quite powerful tools, and it's like one of these things, the more you use them, the more you sort of understand when they work well, when they don't, and stuff like that. All right, so just to finish off this low fidelity prototyping set of lectures, is I just wanted to talk about experience prototyping. Now, experience prototyping was coined by these guys. I'm not even going to try and pronounce Suri and Bushnell. I'm not sure, but they came up with this idea of experience prototyping, which is sort of the new wave of how to prototype, or how to prototype, yeah. So, you know, we've looked at a bunch of things, how we can prototype using low fidelity software. We can get users involved or the end user involved and clients. We can do role playing and all this sort of stuff to try and recreate certain aspects of a design or explore certain aspects of a design. And what these guys were talking about, or what they thought was that really you can't, it's quite difficult, especially when you get to more complicated things, it's quite difficult to segment out the product or whatever it is you're trying to build from the ways it gets used and the context it gets used in. So even designing something as simple as, well, it's not particularly simple, but designing something like a phone, if you really want to explore all facets and all aspects of it, you've got to look at every context that people might be using the phone in. So, okay, it's one thing for me to be sitting here and tapping away on my phone, but a lot of people use them when they're walking, when they're on things like public transport, which brings up other questions again. There's a lot of sort of cultural and social things which come in when you're talking about any sort of interactions in public. So for example, if you go on the London Tube, their train system, you'll notice everyone sits very quietly, doesn't make eye contact, doesn't acknowledge other people on the tube. And so anything which uses voice recognition or something like that, you know, is not going to fly in London because people don't, you know, even to the point they'll deliberately refuse calls on the tube because they don't want to be heard speaking. Whereas last time I was in the States, I was on a bus and there was literally a woman screaming at her boyfriend down the phone, and everyone else was just sort of sitting there, you know, completely blasé. And it's very different attitudes to the same sort of thing in London, where it's seen as being impolite to have a conversation in public transport, to the US where everyone's sort of like, you know, free for all. I do me and everyone else just worry about yourself sort of thing. So taking into consideration things like that, which may not be immediately obviously important at the start. If you're building an app which only works with voice commands, you've basically said, okay, no one in the UK is going to be using this on public transport. So if you're building a transport app which only responds to, tell me how do I get to Piccadilly Circus, you're probably going to find that you don't get a lot of uptake in the UK. So looking at the context and the wider experience around it is what experience, or through designing a product, is what experience design is looking at. So they say in the paper, the experience of even simple artifacts does not exist in a vacuum, but rather in dynamic relationship with other people, places, and objects. So another example, I don't think I have the slide anymore, but it was the example of looking at a planner, so a day planner sort of thing before everyone was using cell phones for that sort of thing, and exploring some of the context of use. So is it a business person rushing from meeting to meeting, having to do everything on the fly? Is it somebody who's got a bit more free time but perhaps don't have their own office, so they're working predominantly in cafes and in public spaces? Is it a stay-at-home parent who's also running a business on the side and they're having to constantly do things one-handed because they're dealing with their child with one hand while trying to organise their day with the other? Looking at the experience of the users and how that interacts with them and other people that they're dealing with, the places that they're in, other things that they're having to take care of at the time. And as well, people's experience changes over time as it is influenced with variations in these multiple contextual factors. It's basically impossible to try and map out every possible use case, every possible context, every possible scenario, but it's worth at least trying to look a little bit out of the box of, okay, we're designing this phone for business people, because chances are they're not going to be the only people buying it, so you're going to want to make sure that you at least consider a few use cases outside of that, and see if there's anything about your design which doesn't work or could be improved slightly, which makes it a much more valuable proposition for people in this area without diminishing the usefulness for people in this other area. So we have a couple of examples coming up which are really interesting. They're more looking at less about a product and more about less about, I guess, designing a product and more about prototyping to gain empathy effectively, or to gain understanding, which hopefully will make this a lot clearer. So yeah, more and more we find ourselves designing complex and dynamic interactions with converging hardware and software spaces and services. So these days, and I think we get back to this when we talk about or Niels talks about the hardware stuff, but these days you don't buy a piece of hardware. You don't buy a phone necessarily because it's got the fastest processor or the best graphics processor or XYZ. You're looking at things like, oh, okay, so it's running iOS or Android, which now you've effectively coupled the hardware with the software it runs on it. Then perhaps you're looking at services. Oh, I've got iTunes on here, all my music's already on iTunes, so if I buy an Apple phone, that makes sense. So now it's not just a piece of hardware and a piece of software, but we're looking at the services which are related to it as well. Oh, I've got an Apple TV at home, this will pair with my Apple TV and allow me to stream stuff straight from there. So we've got this, I'm no longer just buying this because it's got a good processor and stuff in it. Instead it marries into the rest of my life. Oh, it connects to where the repository that has all my music in it, and it connects to my TV, and it connects to my car, Bluetooth, and all these various things that suddenly we have this ecosystem of products or ecosystem that everything ties into. So trying to explore that entire experience becomes more challenging, but also in some ways sort of can add a lot of value to a product. So the idea behind experience prototyping is that we're focusing on exploring by doing. So we're trying to experience subtle differences between various design solutions. So this is one which is, I think, really sort of exemplifies the concept of experience prototyping. And it's quite a clever idea and really, really simple to get working. So the motivation behind this from memory was they were looking at what it's like to have a defibrillating pacemaker in it. So is there so I guess the question is looking forward from that. If you are a patient who has a heart problem and needs, these emergency IED kits that you can attach to yourself. So I'm starting to have a heart attack, I can recognize that, I can attach this to me, and it will shock my heart back to a normal rhythm, which will keep me alive until the ambulance gets there. So we can think about, okay, we need to design this thing so that it's easy to attach to the body, that you can just push a button. And the new emergency defibrillators are pretty amazing. Like literally, they have all the instructions written on the outside, designed for people who've never had any first aid training. You just stick them to the person's chest, push the button and stand clear, and it will not only shock them, but it will also monitor their heartbeat, so it shocks them in the right place. And I can't remember the exact number, but like even one life saved, is a pretty big deal. But they're talking thousands, tens of thousands of lives saved because these machines have been designed to be so easy to use. But the idea behind this experience prototyping is they wanted to explore what sort of situations people would be in. So we're really trying to gain a greater understanding, a greater empathy, greater understanding of the domain, where people are likely to be, what they're likely to be doing in the event of having a heart attack. So what they did is they gave everyone a pager, and at random points, day or night, whatever a pager, a notebook, and a camera. And at random points, day or night, whenever, if you take part in this, you have to accept that you've effectively given up free time. You'll get a page, and you have to take a photo of where you are, and you have to write in the book exactly what you're doing, who you're with, what's going on, all this sort of stuff. And it's not like, oh, I'll get back to that in 30 minutes. You have to do it right now. And the idea behind this is they wanted to simulate this idea of you can have a heart attack anytime, any place. Obviously, certain things are more likely to make you have a heart attack, but it can strike at any point in time. So if by doing this, we can tell people, go out and live your ordinary life as you would, and when you get a page, you have to do this. And so you start getting a lot of feedback from people. I was in a restaurant, I was out at dinner, and this happened. And by giving them the thing of, when we page you, you have to imagine you're having a heart attack and write it down. You start getting all this extra insight. Okay, I'm in a public space. What do I do? Am I going to have to rip my shirt off and like stick these things onto me? How do I feel about that from my own self-consciousness? Am I going to risk my life trying to run to the bathroom to deal with this? Is this something that, these are questions which we have to, when we're designing something, is somebody's life worth more to them than the potential of being embarrassed of having to take off their clothes to attach these probes to their skin? Is there a way we can design the system so that this is no longer an issue? Perhaps there's some way that if people are going out for dinner, we could have them attach the probes beforehand, and then they just have to plug it into the device and push the button. So that way, little things that you might not have otherwise thought about. And it's as simple as just giving people a camera and a notebook and a pager, and just every now and then just being like, oh, let's page this person. Ask them what they would do if they were having a heart attack right now. Like how would they deal with it? There are times when obviously this wouldn't happen. So this actually happened to a friend of mine's father. Was driving a car and had a heart attack and crashed his car and died. But looking at, so obviously there are times when it's perhaps not that feasible. He didn't realize he was having a heart attack and just lost consciousness. And by the time the paramedics got there, he died. But perhaps that's something, having people run through this, you're almost guaranteed eventually going to strike someone who's driving a car. And then there's questions around that, again, of, is this the sort of thing that we're going to ask people, get out of the shower in the morning and attach these probes to you, and then just leave it, have the cord hanging down, kind of like I've got the wire for my mic hanging out the bottom of my shirt. So if I'm like, oh, okay, I'm starting to get a really sore chest, I can just keep the device in my pocket like a cell phone, plug it in, push the button, and away we go. So here's another example that I'm just going to play the video on because it, again, illustrates the concept perfectly. And the good thing about this one as well is that it is not, I know a lot of my example, I think makes a lot of sense. You're designing a store, you want it to be friendly for people who are elderly and perhaps have physical limitations. So, wear a suit which imposes those limitations on the people who are designing layouts of the stores, and force them to go through it, and it will hopefully provide some extra understanding and inspiration and empathy, such that they will be designing these or laying out these stores with a bit more thought as to what the actual customers are going through them. Or for a more tangible example to you guys, so I mentioned one of the ideas you might look at VR. The VR simulation would be underwater welding. So that's, when there was all the oil spills and stuff, they send these divers down and get them to weld the oil pipes, underwater. You could think about for if you were doing a training simulation for one of those, because obviously it's quite dangerous sending people down welding underwater. You might want to do, obviously, nothing replaces the real thing, but perhaps you can get them some of the skills and experience in VR. Perhaps during the VR simulation, they have to throw on a wetsuit and some diving tanks and a life jacket or something, give them that full experience. It's not like I'm just wearing my normal everyday clothes, wearing a VR headset. Instead, I'm wearing a wetsuit, which is quite tight. Perhaps, you have them jump in a pool beforehand, so they're already wet and cold, and, try and recreate some of these more physical aspects of the experience. And I'd love to see you guys do that as part of your first assignment. If you want to do something like that, actually throw on a wetsuit and do all this stuff and see if there is anything you can learn from that. Like, what is it about this experience that is going to make it challenging to try and create a VR training simulation to deal with that. All right, so just to finish up these things. As our ideas and understanding become more concrete, we will naturally start producing more detailed prototypes to test specific parts of our...
Before departing for their field research.
So this is sort of just a little video which I found a while ago, actually for my design thinking course, which I thought was quite interesting. It's sort of, this is maybe going from the next step where they've prototyped out some ideas, they have a rough idea, and now they're looking at building physical prototypes using everyday bits and pieces that they have lying around to test whether ideas are likely to work. So I think in this case they were looking at building, was it medical tools for third world countries or something like that? So places where they don't have, $500 million CT scanners and access to all these bits and pieces. It's really what is the cheapest, most durable, so stuff that you can take in the back of a car bouncing across the African Sahara for days at a time, so it's not going to perish, it's not going to last. And so these students were tasked with that, and this is sort of after, so this is number 6, making ideas tangible. So they've already been through the brainstorming process and stuff like that. I should try and find the rest of the videos actually. But in this case, they're actually starting to build some physical prototypes of it.
Before departing for their field research, each of the teams must come up with several crude prototypes.
So this is a vertical axis wind turbine. It captures wind by using drag.
So the first prototype we built was simply a balloon over a syringe, and it sort of works when I don't break it.
You can actually turn this device on, and this is why it's called a bubble Cpap device. It actually bubbles. And you can actually increase or decrease that. Oops.
This will be a real kind of epic personal journey for me. I feel like my life is about to change.
So not just medical things, obviously there was a few things around there or there was one example in there of doing energy collection or something, like building a wind turbine out of bits and pieces which just happened to be lying around. There was a couple of medical ones, so a syringe, which is, I'm guessing, with a balloon to try and simulate like a slow release. So if you, rather than having a big IV solution which gradually runs through a dripper to give people a certain amount of medicine a certain time, can we recreate that with just having a balloon or some sort of elastic which gradually slowly depresses a syringe presser? There was a Cpap, which is constant positive airway pressure, so for people who have sleep apnea and stuff like that and tend to, or any sort of breathing difficulty, it's like having a constant air pressure forcing air into your lungs. Their one was a little bit more high fidelity as they had an air pump and stuff in there, but obviously we're trying to get around some things like they had the water bottle there to try and regulate the pressure, so you had a constant thing rather than this this sort of thudding pressure into you. It's more like just a constant pressure, so it's less noticeable. Okay, and that concludes low fidelity prototyping. Does anyone have any questions? No? Okay, so as I said, I'll try and get the assignment out to you guys later today, and there's, it's really just, again, to give you guys a chance to play with some of these ideas. Think about some things, think about how you would prototype, run through, a couple of these prototyping techniques and see if there's anything you can learn. It might be that you say, I'm going to do experience prototyping, again, undersea welding, I'm going to throw on a wetsuit, I'm going to soak myself in water, and then I'm going to, hold some welding gear and see how that feels. Or if you know someone who works in an industry and you might ask if you can go along and they can run you through a simulation and you can try it that way. You might walk out of it thinking, I learned absolutely nothing, and that's absolutely fine. Put that in the report. You're not going to be marked down for okay, I went in, I did this thing and perhaps I didn't get anything out of it. That's part of the process. You're going to fail as many times as you're going to, well actually no, you're probably going to fail 99% of the time and you're going to succeed 1% of the time, because that success is completion effectively. But through all the things that we fail and all the mistakes that we make, I personally believe we learn a lot more from our failures than we do from our successes, and it's only through failure we can reach success. So by all means, if you try something and it doesn't work, don't feel that you can't talk about it, that it's something you should be ashamed of or anything like that. I feel probably slightly differently from a lot of the science industry in that way, in that when you publish a paper, there's always this, and this is a bit of a sore point for me, to be honest. So when you're publishing a paper, a lot of people cherry pick their results, or at least try and put their results in a slightly more favorable to their hypothesis way. I think it is as valuable to say, I did this piece of research and I was wrong, because the whole idea of research is that we are trying to contribute to the global understanding. So if I try something and it's wrong, I've effectively saved all you guys the time and trouble of trying the same thing. So despite the fact I haven't been a success, I've still advanced the global knowledge, because I can conclusively say, actually, there's no value in doing this, move on. And I think being able to do that is, or having that information is as valuable as knowing, okay, well this way works, because I can look at it and say this way works, this way doesn't. So, I don't want to do exactly what someone's done before, otherwise it's not research, but perhaps I can move it a little bit, oh, this person's already said this way doesn't work, so perhaps I'll take the research in a different direction. But unfortunately, it does seem, you will find that most papers paint their research in a favourable way, and you sometimes have to read them with a slightly critical eye to try and figure out exactly what they have chosen to omit about, yeah, our system was, allowed people to do things much faster, and then the question is, yeah, but how many more mistakes did they make? If it's something like typing, if you can type 200 words a minute versus 100 words a minute, but you make 5 extra mistakes, maybe that's not a big deal. If it's something medical, and I can treat 10 patients an hour rather than 2 patients an hour, but 2 of them are going to die, that's probably not quite as acceptable. So yeah, I think personally I'm a big believer in owning your mistakes and owning your failures, because that's part of what makes us better people. Anyway, on that philosophical note, any questions about low fidelity prototyping before we move into software? No? Cool. Okay, so as part of what I'm hoping from the assignment anyway is that you guys, through getting some experience, will have more questions, and there'll be things that you don't understand, stuff like that. So certainly if there is anything you're struggling with, let me know, and I can bring it up in class, send an email out, whatever. This will be, your chance to put these skills into action and figure out what you know, what you don't know, which is kind of the whole purpose of this course. But otherwise, let's move on to programming. Okay, so we're going to start programming with a programming platform called processing. Has anyone ever done anything in Java before? No? Okay, so processing is a language which is based on Java. So Java, I'm sure you've probably all heard of it, is this language which was originally built by, I think, Sun Microsystems, who were then bought out by Oracle. The Java programming language is what's known as an interpreted language. So when a lot of languages, I write them in a form that makes sense to me. So you learn a programming language as you would learn a spoken language or a written language, and you write it, and I, as another author, can read that language and understand what your code's supposed to do. When we are talking about programming languages, what I tend to do is I'll write something in C, C#, whatever, and then it gets compiled, which effectively means it gets translated from something we as humans can understand to something a machine can understand. And the compilation process, the reason it exists is because different machines run in different ways. So we have compilers. I might have a compiler which can compile for a Mac. I can have one which compiles for Windows, for Linux, for iPhone, for Android phone. So that's what, I can't remember what they're called now, but I usually refer to them as native compilation. I'm just blanking on the name now. But Java and processing, which is built on top of it, are what are known as interpreted languages. So they're a little bit different. I write code, and then there's what's known as a virtual machine, which translates things on the fly. So rather than compiling it once and I get an executable which will only run on Mac or only run on Linux or only run on Windows, with Java and processing, we write something and it'll run on anything which has a virtual machine. And that's kind of how Java's been so successful, because people have ported the Java virtual machine to everything you could imagine. And I'm not even joking there. There's like, smart fridges running the Java virtual machine, car stereos, TVs, DVD players, just about anything which has a microprocessor in it. Someone has probably written a Java virtual machine for it, so you can write some Java code and it'll run on there. Obviously, certain things won't work if it doesn't have a display. It's a DVD player and it's only got that tiny little display. You'd write a Java graphics app and it won't do anything because there's nothing for it to display on. But that's why Java's been hugely successful. However, Java they used to teach it in first year computer science at Canterbury for quite a while, until they eventually ditched it for Python, because to write your first program in Java, so let me just, how big is mine? It's too small. To write your first, what's known as hello world, which is always sort of the first thing that we write in a programming language. So it's just a program which literally just writes out hello world. In Java, you have to write public static void main. something to that sort of extent, and potentially even more than that. That's roughly it. So to try and explain to somebody who's never written a line of code in their life, okay, what does public mean? What does static mean? What does void mean? What does int mean? What do these square brackets mean? What do these round brackets mean? What do these squiggly brackets mean? What is system? What is out? What is println? Why is this in quotation marks? What is a semicolon at the end? What are these circular brackets here? It's a lot to explain to just get the words hello world to pop up on the screen. And unfortunately, there's no other way to do that in Java. You're kind of stuck doing it. So processing was brought out to basically sit on top of Java, allow access to a lot of the Java stuff, but scrape away a lot of that stuff that has sort of come along because Java was never really designed as a language for beginners. So processing is an open source, cross-platform, multimedia programming language. So open source means that basically anyone, well,
it's available for like even the people post it and like you can pick up stuff online.
Yeah, I mean, open source doesn't necessarily have to be free. And there's different definitions of free when it comes to software. But what open source means is basically you can download the parts that allow you to build processing and you can modify them. So if you find something which doesn't work, you are free to go in and fix it. You're not stuck relying on it. So you think about things like Windows or Word or something. There's something which crashes all the time. They're not open source, they're closed source. You're stuck. You send an error message to Windows and say, please fix this. It might take them a week, it might take them a month, it might take them a year, they might never fix it, and you just have to live with that bug for the rest of your life. With open source, if you're a good enough programmer, you can go and you can fix it yourself. You're not actually reliant on anyone else. Likewise, you can add features, you can do whatever you want with it. The source code which allows you to make processing is available for you. Cross-platform means that it will run across a range of things, so it's not Windows only, it's not Mac only. Processing runs Windows, Mac, Linux. You can build stuff for iPhone, Android, a whole range of things. And from the nature that, as I mentioned, it is based on Java. So as long as the Java virtual machine runs on it, you can probably get the processing stuff to run on it as well. And it's a multimedia programming language. So I still remember bits and pieces of Java, even though I learned it a long time ago and barely ever use it now. But doing anything, even displaying a picture on the screen in Java, you have to import a bunch of libraries, you have to write all this code, all this stuff. In processing, it's like one line of code to display an image. So the whole thing has been designed to do everything multimedia based, so pictures, video, audio, interactions, so mouse, keyboard, all that sort of stuff is usually one line of code will get you what you're trying to do. So it's been designed to try and make people productive effectively. And in particular, it's been referenced as a programming language for artists. So it's something that you can very quickly be quite productive in without having to spend a lot of time learning a ton of useless stuff just to get you to that first barrier. So what is processing? It is a code editor. So I opened this thing up before. This is what processing the code editor looks like, or sometimes they're called an integrated development environment or an IDE. So lots of languages will come with an IDE, or a company will produce an IDE. So processing comes with its own one, which is nice because it's all set up and ready to go. You download one thing, or one zip file, you unzip it, you run the executable, and you're developing and processing. If you wanted to write in, say, C++ or something, Microsoft provides Microsoft Visual Studio, but which you purchase that and then you download it and install it and it can do some stuff. But then there's like Eclipse, NetBeans, like a ton of other different editors which all kind of look the same, all do different things. Some are free, some cost money, some are open source, some aren't. Processing comes with its own, which is good because it means we can download this and just start using it. We don't have to worry about setting it up, having to download compilers and all sorts of bits and pieces. We just go to the website, and I'll show you that in a minute, and download it, and away we go. It comes with a set of basic libraries. So when we're talking about libraries from a programming standpoint, basically we're talking about a collection of functionality that someone's thrown together. Usually the functionality will be related. So we might get a library for playing videos, and in that it will be able to load a video, it'll be able to play a video, it'll be able to fast forward, rewind, pause, stop. All this functionality will be within this library. The script compiler is basically allows us to take the processing code we've made and produce an executable, so a piece of software that other people can run even if they don't have processing. So we can actually build an application and send it to somebody else, and they don't have to have processing. They can run it on their computer just as they would run any other application. And it also has an applet exporter, so Java does actually run on the web as well, and as a result, so does processing. So we can produce an application that I can send to you guys and you can run on your computer even if you don't have processing installed. But I can also export an applet, which is something that I can put on a website, and so I can actually run processing code on a website. So you go to my website, www.mhitlectures.com, not a real website, or at least if it is, I don't know what's on it, so don't go there. But I could put these examples on the website and you guys could run them from within the website, and we'll see that in a minute. Okay, so processing is at processing.org, or if you just Google search processing, you will see it. So the website is, fairly normal. There's not too much exciting going on in there. The first thing we're going to look at is downloading processing. So you'll see the latest version is 3.5.3, which I finally got around to downloading this morning. So for example, the Mac OS one, I just click on it and it will download a zip file, which I already downloaded earlier. So there it is there. And if I click on that, it will just give me that processing application, which I can open. And that's all there is to it. Likewise on Windows and everything, I think you have to just unzip it into a folder because it's got, in Mac you have an app file which is kind of like a zip file in itself, but it has a bunch of stuff. In Windows I think it's got a few bits and pieces. So processing is free. You'll notice on the next page that from here you can choose to donate. You don't have to obviously, but if you really love it and you're feeling particularly generous, go right ahead. And then there's a bunch of other stuff. So processing, as I said, is they talk about it as being a tool for artists. So they have quite high up this exhibition thing, which is showing various exhibitions at things around the world, which have been built in processing. So this is page 15 now. But if we open one of these up, just to give you the sort of idea of what some experts are doing in processing. So this is particle flow, a kinetic motion study. So some sort of massive big rig on actuators which allows it to move around and a little bee thrown across it. You guys won't be building anything this cool for your assignment, and I apologise about that. Well, you're welcome to. But it allows you to sort of see some of the stuff that other people are doing with the processing language. Some of the sort of stuff you get to and you wonder whether processing was really the best choice, but the fact that it's possible to do this sort of stuff.
One, the driverless car one below this last row.
That one?
No, below.
Oh, bottom row.
The middle one. In which the hand is showing. The last. The hand.
Oh, that one?
Yeah.
Oh, I see. Right.
This is for a car or?
I have no idea.
I think this is for the. This is the communication with the driver. In a driverless car, you communicate with the car.
Okay.
That's very cool.
So there we go. Some stuff other people have heard of before. So yeah, there's lots of stuff in there if you're looking for inspiration. But what's quite cool, so the books you guys have got cover processing, like from never written a line of code before, right up to being quite experienced. So there's a lot of stuff in there, but they also have, actually we'll start down here, they have a lot of tutorials. So hello processing, it's a long-standing meme, joke, whatever, in the programming world, that the first thing you do in any new language is write a program to write the word hello world. So hello processing is their introduction. But then it goes on to a bunch of stuff, welcome to Processing 3. So Processing 3 came out a couple of years ago now, but yeah, it sort of talks about the difference between them, how to debug, and then there's a bunch of tutorials talking about various different things that you might like to do. Each of these is obviously focused around a certain topic, so if you're interested in learning about sound, there's a tutorial which will go through all the bits and pieces. I haven't read most of these tutorials, so I have no idea about the quality of them. But you can see here this goes into, by the looks of it, a fair amount of theory. So they're looking at sound and musical informatics and how pressure affects a waveform and the time domain plot of note A4 bowed on a cello. So obviously quite a lot of detail there that you don't need in order to actually make noise play and processing. They have some code examples down the bottom, but to be honest, again, to play a sound file and processing it, it's very basic, is probably 3 lines of code. So these tutorials go in quite a bit of depth. You have examples as well, which are a bit more simple and tend to just focus on one sort of sub-point. There's a range of books, so we'll notice somewhere in here will be programming interactivity, which also covers other things. It's not just processing books, so it's kind of good. But they have as well reference manual. So this is what I was mentioning at the end of the book. They have the reference manual. And if I'm looking at doing something, okay, I want to do some input, mouse input, I can look here and see here are the names of the functions that are in processing. So there's a mouse button thing, or variable in this case, which we'll talk about what a variable is later on. And I can see some examples, get a bit of a description and see some related things. So even though I've been using processing for a while, and I don't use it day to day, I only really use it in the MHIT course, I still find it quite useful to be able to go back to the reference and say, what was the name of that thing again? Or, you know, I remember it was something to do with this, look in mouse button, oh, there it is, it's mouse X, mouse Y. There's, in this libraries thing, you'll see there's a bunch of libraries, so by default, processing comes with a few, so from processing you can actually create PDF files if you want. So because it's a visual or multimedia programming language, you often do a lot of visual stuff. So you might do some beautiful things and decide, you know, that would make a great poster. You can export that to PDF. So PDF is a vector graphic. So when you talk about graphics, you have scalar graphics and vector graphics. Scalar graphics are made up of pixels, so you have a bunch of pixels, and as you make it bigger, usually the pixels just get bigger. So they get blockier and blockier and look like they're made out of Lego blocks. Vector graphics are mathematical functions. So as they get bigger, the value of the mathematical function just gets bigger, and when you draw them out, they're nice and smooth. So if you had a circle, a scalar circle which was quite small and you made it big, it would look very blocky around the outside. If you had a vector circle and you made it bigger, it would still look like a nice smooth circle. PDF is vector, so you can just basically make your graphics, export it to a PDF, and then blow it up to A0 size or as big as you want, and it'll still look nice and smooth and beautiful. There's some stuff for networking, so if you want to communicate over the network to another processing app or an autonomous car or whatever, there's a library which comes with processing which does that. SVG, which is another format for scalable graphics. Serial, so when you get to dealing with Arduino, serial communication is those really old square plugs. These days we do a lot of serial over USB, so your Arduinos will be using serial over USB. So you could have, and for your assignment you will do this whether you do it using the native serial or a library which sits on top of that called Fermata, is Niels' decision effectively. But it basically allows your processing to communicate with your Arduino. So you could have your processing thing light up some lights on your Arduino, or you could have it, you push some buttons and it does something on your processing sketch. DXF is again another, I think that's more for 3D. Video, which allows you to read video files and play them. Sound, which allows you to read audio files and play them, and also has a bunch of other stuff for making sounds. And some hardware I/O, so stuff for processing run on Raspberry Pi. So that's the little, it's a little microcomputer which is about a little bit bigger than a credit card. They're about $30. If you guys end up doing stuff with the Raspberry Pi, I'd be very happy because Raspberry Pi is really cool. But then, so these are the ones which come with processing by default, but there is a ton of other libraries for doing a whole range of stuff. So I am a lazy programmer, and I would encourage you guys all to be lazy programmers as well. If something exists which does what you want it to do, use that. There is absolutely no purpose rewriting everything from scratch. If you want to do something, let's see, you want to do something in sound, for example, so you want to make a nice visualization for sound, which looks like an oscilloscope. So, you know, one of those things which has the lines on it, so you can see when the audio comes out, it has the squiggly lines. Why bother writing it yourself? There's XY scope, which somebody has made. Hopefully, I'm just picking this one at random, which will do that for you. So there is really no point you guys writing it, download the library, and do something cool with it. Okay, no, so I was wrong. Actually, this is a library for processing which will export stuff so you can plug your processing thing into an oscilloscope and draw graphics on it like this. Whether that's ever going to be useful or not is debatable, but it's there. But this is probably not a great example because I can't ever imagine the need for you guys to write these things yourself. But if you're ever at the point where you'd really love to draw some stuff on an oscilloscope using processing, don't write it yourself. If somebody else has done the work for you, steal as much as you can and make the part that you do the part that is different. And yeah, that goes for assignments as well. So if you can find something which gets you 80% of the way, take it, credit it, of course. You know, I downloaded this file from here, but then what I'm interested in is that extra 20%. This isn't an algorithms course. I'm not interested in you guys being able to implement everything from scratch. I'm interested in you guys finding what is available for you to use and finding really interesting and creative ways of working with that sort of stuff. And I might give you a little homework assignment over the weekend, which will be exactly that. Go down, find some existing processing source code, try and understand how it works, and make a small modification to it. It's like a 15-minute job, but just, again, to force you guys to download processing and actually have a play with it. All right, let's take a short break there before we actually get into programming. So go get yourself a cup of coffee or water or whatever, and we'll meet back here in about 5-10 minutes. Cool, okay. A black box at the top. Okay. I'm not quite sure what's going on, but okay. So we've talked a little bit about what processing is, what libraries are, script compilers, blah blah blah. Doesn't matter at this point in time because we'll come back and look at all those things later. But what I thought, it was probably a good time to start talking about some programming basics. So for some of you, this may be very basic if you've done any programming before. For some of you, this may be completely new and novel. We have now plenty of time to cover this. So we used to, unfortunately, because of the amount of content in this course, used to sort of had to go through this at a fairly decent pace, but because Anthony's taken over some of the extra material from the low fidelity prototyping, we actually have quite a bit of time to go through this now. So if there is anything that I haven't explained very well that you need more help about, I would really like this to be a back and forward, bit more interactive. So please do, ask questions. Don't be afraid. We're all here to learn. So as I mentioned, there are tutorials and reference material on the site, which will cover a lot of what we're going to cover today in various levels, sometimes more detail, sometimes less detail. So if I've done a terrible job explaining something, please do let me know. All right, so let's open up processing. And for those of you who have your laptops here and have installed processing, you're welcome to follow along. For those of you who haven't, bring them next time. We're not going to cover anything too tricky today, so it shouldn't be too bad. But let's have a look, and please do let me know if you can't read the screen. Hopefully that's big enough. We're going to do our first program, Hello World. So the first thing we're going to write is println. Now print, well actually we'll start with print because that's slightly easier. So print, like the name suggests, print something. So print is a function. So what a function is it's essentially a collection of things that processing knows how to do that's all been wrapped up into a nice little bundle that we can tell it to do something. So we denote functions by having circular brackets around them like this. So this is basically saying, I want you to execute the print function, and I can pass in what are known as arguments. So effectively, an argument is some information to give to the print function to tell it how to do its job. So in this case, I'm going to print hello world like this. And you see I've put hello world in quotation marks. And what these quotation marks mean is that this is an argument which has a certain type. So when we're talking about programming, every piece of data has a type. It could be a number type, which means that we know that it's going to have a number in it. It could be a floating number, so it could be a fractional number. It could be a character. It could be a string, which is text. But everything has a data type, and the reason for that is we need the computer to know effectively what a variable is. So actually, let me finish with hello world because we're going to talk about variables in a second anyway. But effectively, what we've done is we're telling this line of code here says execute the print function, and we know it's a print function because it has these circular brackets. And give the print function this string. So a string is just a collection of like letters or numbers. It's just a piece of text effectively with hello world. And the last thing, because this is a Java-based language, which is effectively a C-based language and so on and so forth, we end every statement with a semicolon. So that tells the computer this is the end of the thing. And if I hit play up in the top corner there, you'll see a few things happen. So this little window pops up. So processing, because it is a multimedia language, will always give you a window. Even if you don't want it, it will pop you up a window. And by default, I think that window is 100 pixels by 100 pixels and everything. So we'll come back to that a bit later. Let's just ignore that for the moment. But we'll see down here in the console part, the hello world. So effectively what has happened is I've executed the print function with hello world, and then processing's gone off and said, okay, the print function tells me how to put things on the screen. So I have printed the text hello world on the screen in the console. So I can change that to whatever I want. Hello MHIT 603. And again, if I hit the run button, we'll see hello MHIT 603 pop down there. So we've effectively written our first program now. And it's a lot simpler than the public static void main in args. Thing we had to do with Java. We can just write a piece of text or write a command and it will execute that command. Okay, so the reason I wanted to show you this print function before we touch on anything is because printing stuff out to the console like this is something which almost every language supports, and it's a really good way of figuring out what's happening in your program. So I can, and actually, maybe now that we've got time, I might put in some debugging stuff because it's something that often gets overlooked. So debugging is basically trying to find problems with your program. So if your program isn't behaving in a way that you would expect it to, most programming languages, and I think processing included, includes debugging, which allows you to sort of step through and see what's happening one at a time. Because normally when you run a program, it'll just do everything and then it'll finish. And it's kind of hard to tell where exactly it's gone wrong. But I will throw in, maybe try for Thursday, some debugging slides so we can learn about that a little bit as well. But printing is a really good way for us to figure out what's happening because we can put in as many print statements as we want, and we can print out the value of variables so we can see what's stored in the program's memory and everything at the time. Okay, so now that we know we can use print to help us figure out what's happening in our program, let's jump back to our slides and start going through it. So the first thing I want to talk about is variables. So variables are basically just a pointer to a piece of memory on a computer that will store some data. So everything in a Yeah, we'll talk about it now a little bit and then we'll come back to it. So if you think about our computer, we basically have the RAM in the computer, which is random access memory, and that's just a bunch of space that we can put data into and read data out of. So when I create a variable, let's say I'm going to create a variable integer, and I'm going to call it my integer. Again, I'll come back to what this is at the moment. That's basically telling the program, I am going to want to do something with an integer. So an integer is just a whole number. So it could be a positive number, a negative number, or 0. So -5, 0, 1,263,000, any of those things. Basically, we're saying we want to have a place we can put a number in our memory somewhere. So saying int, myInt, will tell it, I want a variable of type int, so an integer, and I'm going to refer to that integer as myInt. So I can set the value of myInt to something. I can ask to be told what is stored in myInt. Think of it as just, you know, a little cubby hole called myInt, and if I say to you guys, what's on myInt, you can go over, look in that cubby hole and say, it's the number 5. Or I can say, hey, can you put the number 32 in myInt, and you go over and put it in there and you can read it back later. And effectively what is happening is when I do that, the computer will set aside a little bit of memory, and it'll say, okay, that memory is known as myInt, and anything that I put into myInt will be in that piece of memory. Anything I read out of myInt will be in that piece of memory as well. That becomes more important when we start getting to arrays a little bit later on, but let's just you know, hopefully that makes sense. You can think of the computer's memory as a massive big thing of cubby holes or little boxes, and you can say, I want to label that box myInt, and then when I put stuff into it, it'll go into that box. When I pull stuff out, it'll come out of that box. Okay, so let's create our first integer, int. So we're going to tell it it's an int. Now different data types have different sizes and they're treated differently. So we need to be explicit. Some languages you don't have to. Processing and the family of languages that it comes from, which I will call C programming languages, because C, you might have heard of C or C++ or C#. C is sort of the biggest of those. It was the first, it was like 1987 or something. Still used today. You know, that's almost unheard of in technology. And all of these other languages have been inspired by it. So if you guys get to the point where you can read and write processing and you're really comfortable with that, you can pick up a C program and probably read about 80% of it. So, you know, they're all from the same family. They're all very similar. They look very similar. There's a few little differences here and there, but you'll be able to read about 80% of, you know, a beginner's program in C and in Java and in C++ and in C#. They all look quite similar. But this C family of languages, they all need you to specify, when you're creating a new variable, you need to specify what type of variable that is. So in this case, I do that by specifying what data type it is, so an int. So this is going to be a whole number, which can be negative, 0, or positive. So int, myInt. So that has basically done exactly what we've set there. When I run this now, nothing's going to actually happen other than print hello MHIT 603, because I still have that line of code in my program. But the computer, we can now safely assume, has put aside a little piece of memory for me to put some stuff in myInt. So what I can do is I can set the value of myInt by saying myInt equals. So say I want to put the number 5 into myInt, I just say myInt equals 5. And now, again, when I run this program, sitting in my little myInt box will be the number 5. It's not actually doing anything with it, so I don't see any change in results, but we know it's there. So this print statement, as I mentioned, can take arguments, which is basically what I want it to print to the screen. So I can tell it to print myInt. So, and the print statement is smart enough to know that when I say print a variable, it should look up what's inside that variable and print that to the screen. So this program now, we are saying put some space aside for an integer and call it myInt, set the value of myInt to 5, and then print out what is the value of myInt. And hopefully you guys, as you guys were expecting, we see the value of 5, because we know we've stored the value of 5 in myInt and then we print it out. So programming is an exercise, and there's about 1 billion ways to do exactly the same thing. So say this is way too many characters for me. I can actually do the same thing by telling it when I create my integer called myInt, set its value to 5 straight away. So these two examples actually do exactly the same thing. In one, we create the integer and then set it to 5, and in the other one, we do that all in one step. We create the integer myInt and set its value to 5 straight away. And likewise, if we run it, that's what we get. So we could do some more interesting things. We could say myInt equals 10, and now when we print that, it will print out. What you guys tell me? 10, yep. That's right. So we set it to 5 initially, but then we change its value to 10. It prints out 10. And likewise, that will happen to anything. So I could say set its value to 5, then change its value to 10, then change its value to 12, and when I print that out, it will be 12. That's right. Love the enthusiasm, guys. It's only going to get better. All right. So we can do some more interesting things. Let's say we want to increase the value of myInt by 2. We could have something which looks like this. So what we're saying now is set the value of myInt to be its current value, so get its current value and then add 2 to it, and then store that back in there. So if myInt is 5 to start with, print myInt will be 7. That's right. So effectively, we've got the value of myInt, which is 5, added 2 to that, which is 7, and then stored that back to myInt, and then we print that out. We could also do that in the print statement, because the print statement's quite clever like that. So we could just say print the value of myInt plus 2, and it will calculate what that is before it prints it out, and we will get the value 7 again. Okay, so that is an integer. So as I said, an integer has to be a whole number. It can be a negative number, it can be 0, or it can be a positive number, as we've seen before. But it cannot be a fractional number. So if I try and say int myInt is 1.5, you see it's put this, it doesn't look very much like it there, but on my screen it's a squiggly red line, like when you misspell a word in Word or whatever. And if I tap on that, you can see down here, type mismatch, float does not match with int. So type mismatch, I mentioned before that all variables have to have a type, and that's going to be the type of data which is stored in it. So type mismatch is telling us that I'm trying to put a data type of one type into a data type, and I'm trying to put a piece of data with one type into a variable which holds a different data type. So in this case, it's saying float, which we haven't heard of yet, but we will in a second, does not match with int. So we've got an int variable here. We're trying to stick something in here which isn't an int, and it's telling us that you can't do that. And in case you guys haven't already guessed, the fact that it says float does not match with int means that fractional numbers are called floats. So if I change this now from being an int to a float, you'll see that error disappears. And when I run it, it'll now be 1.5. So it's called a float because it's a floating point number. It comes from this long line of very confusing definitions and descriptions. But all you need to know is an integer is a whole number, and a floating number or a float is a fractional number. And likewise, that can be positive, it can be negative, it can be 0. What is also kind of interesting is that there is almost this hierarchy of data types. So a float can't be an integer. You guys are storing, you're a variable, you're integer variables, and I tell you store the number 1.5, what do? You guys don't know how to store a fractional number. So do you store 1? Do you store 2? Do you round it? There's actually no way of knowing, and that's why it will basically throw its hand up and it will say, I don't know what you want me to do with this. Am I supposed to just cut off everything after the decimal point? Am I supposed to round it? That can cause very different behaviors. Rather than just taking a guess, I'm just going to say, I don't know what you want me to do with this. There's a type mismatch. However, as I said, there is a hierarchy. So if you guys are storing floating point numbers, and I give you just a plain integer, so I give you the value 1, you guys actually can figure out what to do with that, because 1 is actually the same as 1.0. So if I tell my int to be actually that doesn't make sense that it's my int anymore. My float, if I give it the value of 1, and variable names mean nothing, so I can give that name of whatever I want, which is why it worked perfectly fine when I had my int, even though it was a float. So I give it a value of 1, and it's smart enough to know, well, 1 is exactly the same as 1.0, so I'm just going to say it's 1.0 and be done with it, and that will be just fine. So floating points can store integers. They will just turn them into floating points, but integers can't store floating points, because even if it's the case of something like 1.0, it will still complain, even though we as people could say, well, 1.0 is the same thing as 1. It's just going to say, I'm not doing it. I'm not going to allow you to convert from a float to an integer, because more than anything, it's probably a safety thing. If I've said 1.0 up here, chances are, in my mind, I'm going to be working with floating point numbers. So later on, I might do something like try and say my float equals my float plus 0.5, and then obviously that becomes an issue, because now, even though 1.0 can be treated as an integer, this would give us the value of 1.5, and that can't. So it's just going to err on the side of caution and just say, if I'm an integer and you're trying to give me a float, I'm just going to throw an error, and you can deal with that.
You can see casting in some way now.
Yes, so we will get to casting right here. Yep. Trying to ease you guys into it. So yeah, as I mentioned, variable names can be absolutely anything. And as far as the computer cares, it's all the same. It's just a label that sticks on there. It has no meaning. There are restrictions. I can't have a variable number or name which is a number. There are certain characters that I can't throw in there. But generally speaking, if you stick with just writing out text names for them, that will probably be fine. You can have like my int 1, so you can have a number at the end of a variable name, but you can't have it at the start. There's a few rules. My advice to you guys would be make your variable names descriptive. Don't call this, like I could just say int x equals 1, print x. And then you write 1,000 lines of code and I ask you, what does x do again? And you have no recollection because it doesn't actually tell you anything. So I would recommend giving them names which mean something. You'll notice when I was writing them out, I tended to write what's known as camel case, which is your first word starts with a lowercase and then every additional word starts with an uppercase. Purely convention. The computer does not care. It does not care if I write in camel case. It doesn't care what I write, as long as it always starts with a letter and stuff like that. I don't know. It was drilled into my brain when I was learning programming, use camel case, so I can't not use it now. For me, if I write my int with a capital M, the computer doesn't care, but I look at that and I'm like, it's not supposed to have a capital. But you guys are free to do whatever works for you. Again, this is not a computer science course. I don't care what you use. I don't care if it's inconsistent. As long as you guys can understand it, that is number one importance. If I can understand it, that is an additional benefit. For your assignment, there might be like 0.5% that your variable names make sense. So rather than calling it X, you've called it, length of string or something, because that tells me that, in this variable, I would assume that it would hold the length of the string because that's what the name is. Whereas if you give me X, I have no idea. There was a computer science lecturer in the computer science department who unfortunately just passed away a few years ago, called Tad, and he taught algorithms, and he only used single letters for his all his programming. until he ran out of single letters, because obviously there's only 26, and so then he'd start, his first variable was always x, and then he'd go y, z, a, b, c, d, blah, blah, blah. And then he'd go around, and when he'd used all 26 up, he'd use x, 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 y, x, z. And I actually taught his, I was a tutor for his course for a while, or like a lab tutor, and it was awful. Because I would have to, he'd give me all his, you know, they were algorithms, so they were often quite sort of challenging to understand to begin with, and I would have to translate them for students because they'd be like, what is x? And I'd be like, well, x is actually the number of times we've been around this outer loop. What's xx? Xx is the number of times we've been around the in loop. What's xxx? Xxx is actually something completely different. Don't worry about xxx. So please do use sensible names. In the slides here I've used x and y just to, you know, go against what I've just told you guys, but don't do that. Okay, so there are other things. So we can deal with whole numbers, we can deal with fractions of numbers. What about other data types? So say we want to represent a single letter. We have this data type called char, or character. Would it be? Yeah, no. I was going to say if it's character, would it be car? But that's neither here nor there. So we have this data type, my character, or char, which represents my character, and in that I can put a single character. So I can put the character x, and I can print it out. So if you remember before, we had hello world. I printed hello world, oops, and I used double quotation marks like this. This is a string, and it has double quotation marks. So if it has more than one letter in it, you need to put double. If it only has one letter, it has a single quotation marks over it. The reason for that is, if we go back to our RAM in here, let's say we have 1 unit of RAM. So I'm just going to write x here because I'm lazy. So I have a single character x, and I give it the value of x. So what that's going to do, no, I'm not going to do that. I won't be so lazy. My char, because otherwise I'm just going to end up with x written everywhere. So it's going to give me a single piece of memory, pardon me, my char, and it's going to put the value x in there. If I then decide to put a string in, hello string, and I put in that hello world. If one of these spaces is only big enough to hold one piece of text, putting all of these in here is obviously going to require quite a lot of these spaces. So what we're going to end up with is when it sees that we're putting these double quotes in, it says, oh, okay, I actually need a much larger chunk of memory. And we will end up with all of that put in there. So that's why characters and strings are different, because we know a character is only going to be length 1. So when we give it a piece of memory, we know we can give it a nice little piece of memory that only can fit one character in there. When we put a string in, strings can effectively be theoretically infinitely long. Eventually we will run out of memory on our computer. So we know that we need to allocate a lot more memory for it. Likewise, integers, because they don't have a fractional point, are usually smaller than a floating point. So maybe an int takes up this much memory and a floating point takes up that much memory. It's usually not worth worrying about too much unless you're writing massively big programs. Chances are you're not going to run out of memory, but it does happen. But that's, I guess, the reason I want to highlight this is there is a difference between a character and a string. A character can only ever hold one letter, whereas a string can hold theoretically an infinite amount. And that is why we have characters which have these single quotation marks, whereas a string, bless you, a string has double quotation marks. It's telling the computer how much memory you need to put aside for it, one piece or theoretically a lot. And likewise with printing my character, we can print out my string and we will get hello world. So now we have this program now has two variables in it, one called my character with the value x, one called my string with the value hello world, and a print statement to print that out. And likewise I could throw in another print statement to print out my character. And you see something a little bit weird here. We see x hello world. Yeah, so there's no line break in here. Print by itself doesn't have this concept of a line break. It doesn't know that it needs to push return at the end of the line. So what we could do is there are characters which are known as special characters in programming. The one for new line, so basically pushing the return key, is backslash n, sorry, like that, which will basically print out my character x, and then it'll print out a backslash n, which is the new line character, and then it will print my string, which is on these two lines. Or alternately, what we can do is there is another function which is called println, which will print out the string and then add a return at the end of it. So that's supposed to stand for print new line. It's not new line backwards, it's just line, supposed to be shortened at the end. So println will print out whatever argument we give it, and then it will put a return at the end so that we can continue printing. So I often recommend using println over print, because you can imagine this case where I have, let's say, two numbers. My number 1, let's give it the number 1, 2, 3, int my number 2, 4, 5, 6. So now we have two numbers, my number 1, which is the value 1, 2, 3, my number 2, which has the value 4, 5, 6. And if I use two print statements like this, I'm just going to get 1, 2, 3, 4, 5, 6. I know there's two numbers in there. I just have no idea where one ends and the next one begins. Is my number 1 just the value 1? My number 2 is 2, 3, 4, 5, 6? Or is it 1, 2, and 3, 4, 5, 6? Or so on and so forth. So I would recommend always use println over print unless otherwise, unless you need to, effectively. Because at least that way you can look at it and you know that when you hit the end of the line, that is the end of what you were trying to print in that variable. Okay, how are we doing? Everyone still with me? Happy? Yeah? No one's fallen asleep or left the room yet, so that's always a good sign. Okay, so that is a variable. It is a cubby hole in the computer's memory that we can stick some stuff into. Does everyone know what a cubby hole is? No? Yes? So it's cubby hole is probably quite a, I don't know where it originally comes from, but it's fairly common term in New Zealand, but it's basically like, they're sometimes called pigeonholes or something like that, effectively, which is what I was trying to draw there. So when you go to school in New Zealand and you're a little kid, you have a cubby hole that you put your bag into. I don't know where the phrase comes from, but that's when I'm talking about memory. You can imagine this is your computer's memory, and each of these is effectively a variable that you can stick stuff into and pull stuff out of. Okay. Right, if everyone's happy with that, let's have a look at this. Okay, so does somebody, yeah, is everyone happy with these two lines? They can understand what the program is going to do with this. Yep. So it's going to give us two variables, one which is a character or char and holds called my character and has a value x, one which is a string called my string and it has the string hello stored in it. So one thing you might notice, well, maybe you did, maybe you didn't, is when I was talking about int, when I was talking about float, and when I was talking about character, these all start with a lowercase letter. String starts with a capital S. So you may have noticed that, you may not have noticed that. It is deliberate. There is nothing which is not deliberate in there. And that's because int, float, and character are all what's known as primitive data types. So a primitive data type is a data type which basically just stores data. It's all it's able to do. I can put a number into a int. I can pull a number out of an int. I can put a number into a float. I can pull a number out of a float. There's one more on there that I haven't talked about so far, which is called a Boolean, which holds the value true or false. So a Boolean can either be true or it can be false. It can't be anything else. So it's kind of, yeah, the most basic of the data types. But a primitive data type, all you can do is put a number into it or pull a number out of it. A composite data type is what a string is. So again, I'll put these slides online. So you're welcome to write your own notes, but don't worry about primitive blah, 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 because it will be in the notes. A string is a composite data type. And what a composite data type means is that it's kind of a collection of data, but it also has some functions. So we talked about print as a function, or println. So println is a function, and it has an argument that I give it my string, and that will print out something. So a function is a thing you can do effectively, so you can execute it. So string is a data type, which is a composite data type. So it has some data. In this case, it has the data hello, but it also has some functions. So what I can actually do is I can call my string dot, and when I put the dot after it, it's telling the compiler I want to call one of the string's functions. It has a function called length, which when I run it will give me the value 5, because the length of the string is 5 characters. 1, 2, 3, 4, 5. 11 for hello world. 1, 2, 3, 4, 5. We do count space as a character. 6, 7, 8, 9, 10, 11. There are some other functions that I can't remember off the top of my head, but we can find out in a second. So you'll see, this is the, let me zoom this in for you guys. So this is the reference thing for processing. If we scroll down here somewhere, we have data types. We have primitives, so here's all the primitives. So we've looked at Boolean very briefly. We've looked at char, we've looked at float, we've looked at int, and you'll see there's some composite ones down here, including string. And you'll notice all of the primitive ones start with a lowercase letter, all of the composite ones start with an uppercase letter. So let's click on string to find out some more stuff. So you'll see here is some examples of how to use string and so on and so forth. But if we scroll down the bottom, you'll see methods. Methods and functions, I'm going to use the terms interchangeably depending on who you talk to. Some people might say they're different, but effectively a method and a function is the same thing. So you can see these are the methods that string has. So we've already seen length, which returns the number of characters in the input string. There's to lowercase, which will convert everything in the string to lowercase, to uppercase, which will convert all the characters to uppercase. We can get the index of a substring within an input string. We can tell as it equals. We can return a character at a certain index. So let's have a look at one of these other ones. But first, so my string is a composite data type. Putting this full stop here tells me that I want to access one of my string's functions. So println obviously is just a function which exists. We can say println anywhere. We don't need to say something dot println. But for the length thing, we can't just call length because we don't actually know what we want to find the length of. We need to say, I want to call the length function which belongs to my string. And then it knows, okay, well, I want to find, my string knows how to find the length of this. Just like with the println function, so let's do this up here. So in the println function, we know it's a function because it has these round brackets after the name of it. So we have here these two round brackets. Now in println, it takes an argument or we give it a piece of data to tell it what to print. Length doesn't take anything. So likewise, we could actually have a println statement which looked like that, and that would just print a new line effectively. It's printing nothing, then it sticks a new line, or if we have just print with a bracket, it'll print nothing and then return. So when you see something like this, it just means call the function, but don't give it any extra information, just call it. And yeah, that will then return. So I could do, likewise, I'm calling it in the println function, but I could use that anywhere I wanted. I could have a new int, my string length, and I could set the value of my string length to be my string.length, and then that integer I can do whatever I want with again, and that will give us the same value. So essentially, my string.length will just give us the value 11 in this case, or whatever the length is, and I'm free to do with that whatever I want. I can store it in a variable, in this case my string length. I could print it, I can do whatever I want with it. So let's have a look at one of these other ones. So let's look at char@. So char@, if I click on it, will give it some information. But the syntax, so syntax is basically how I use it, looks like this. So we have the string variable name, so my string. We have char@, so let's start writing this out. My string.char@. And then that takes an index. And if we look down here, we can see the index is an integer, which gives us the index of the character we want to get. So in this case, let's just say 0. And let's put that in a println statement so we can see what it's going to give us. Now, so this line here is going to call the char@ function, which is part of the myString variable. And it's going to give it the value of 0, which is going to ask for the character at index 0. Now, in computers, we always start from the value 0. So the first number in a list of numbers is not the first number, it's the 0th number. And then, so if we had a list of numbers 6, 5, 3, 1, 8, if I asked you to give me the 0th number, you would give me 6. If I would ask you to give me the value at index 1, it would be 5. And then 3 would be at index 2, 3, 4. Again, some programming languages start at index 1. They are blasphemous and we do not talk about them. It's one of these things that takes a little while to get your head around, but when you do get your head around it, it just becomes sort of religion. And then you see a language where this would actually be index 1, and all of a sudden you have to completely change your way of thinking about everything because you will constantly get everything wrong. Who made that decision in the first place that it should start from 0 rather than 1? I don't know, but I'm a convert, you know. It's the way I learn. It's the way I would say probably maybe 90% of languages will start from 0. Just get used to it is all the advice I can give, because chances are most things you come across. There are a few languages, I think MATLAB by default maybe starts from 1, which seems horrific because MATLAB is supposed to be like programming for mathematicians and engineers and stuff, and we're getting them off on a bad foot, getting off to a bad start. I think there is a command in MATLAB you can change, one command which will basically start it from 0 rather than 1, so that's fine. But by far and away, most of them will start from 0. Okay, so we have the statement println, call char@ on my string with the value 0. Does anyone want to hazard a guess at what that's going to print?
The first digit, H.
Yep. So the letter H. So we're printing char@ return will tell us what character is at a particular index, and we're doing that on my string, which is the string here. And so if we effectively think of this as a list, this will be at index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that will be 10, which I'm just going to represent with a 0 again. So if I wanted to print out the letter W, what would I put in char@?
6.
So if we put in 6 now, I'm going to just talk about what I just did there in a second, but we'll see the value W printing in there. Okay, so what I just did then, I put these two slashes in here. So at the moment, I've got these numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 in here. And you can see it's got the red squiggly line and it said consider adding equals, because it's telling me you put some numbers in here and I actually don't know what you want to do with them. Maybe you wanted to put something as equal to that. So int x is equal to that. Is that what you were wanting to do? And then I'll tell me I'm missing a semicolon at the end because it's quite pedantic like that. But effectively, I've written something in my code which the computer's not sure exactly what it's there for. Why are these numbers in here? So what I did was I put these two little slashes in there, and you'll notice suddenly the text changes color to gray and everything's nice and happy again. So what these two lines are, it's called a comment. So basically, a comment allows us to put any text we want in our program, and the computer will just ignore it. So comments are really helpful. I would highly recommend you guys use them, because while it may make sense to you what you've written now, come back to it in a year's time and tell me if you still remember what you were thinking when you wrote that. Different people will tell you different things about how much you should and shouldn't comment. I'm happy to do it when we get to talking about functions, do it at a function level. But we'll get into that later. But if in doubt, you know, if you've done something which you're having trouble explaining to someone, it might be worth just putting a comment near it, usually before it, but it doesn't have to be, just explaining what that piece of code is supposed to do. There are multiple ways of doing comments, so I can do this backslash, and anything which follows the backslash will be ignored. So likewise, I can actually put it at the end of a line, and it will ignore everything in that. It's effectively, for the computer, it sees these two slashes and it just deletes everything afterwards. There is, if you have really long comments, you also have the option of doing a slash and then a dollar and then a star, and then anything you write until it sees the opposite at the opposite end, so star and then a slash, will be ignored. So if you need to comment, like write large pieces of text, or sometimes, yeah, sometimes if you want to hide code. So let's say, oh, I've got all this code up here that I don't want to use anymore. I can just stick a slash and then a star and then a star and then a slash, and that is invisible now as far as the computer's gone. So it's often quite useful if you've been testing something and you want to, or you are testing something and you want to remove a piece of code because it does changes things in a way that you don't want to have to think about or deal with at the moment. You know, it might be quite useful to just comment out the code like that. Okay, where are we up to? So, we've looked at primitive data types, so we've looked at ints, we've looked at floats, we've looked at chars, we've looked at booleans, we've looked at the string composite data type. There is obviously a ton more if we look at this. So you can see we've got array list, double list, float dict, float list, hash map, int dict, int list, JSON array, blah, 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 blah. Ton of stuff in there that I'm not really that concerned with. String is really the one that you'll be using fairly often, so that's the only one to look at, but at least hopefully you guys understand the difference between a composite and a primitive data type. Is everyone happy with up to here on this slide? Yep. Okay, so there's one more thing which was mentioned about casting. So let's say, where are we? Let's say I have a floating point, my floating point number. And I, for some reason, really want that floating point number to be stored in an int. So, if I try and assign this floating point number to an int, like this, we'll see again a little error, and I apologize, I don't know that I can actually make that any bigger, but it says type mismatch, float does not match with int. So processing is smart enough to know my floating point number is a float, you've just told me up here, and my int, which was a float, is an int, you've just told me here. I can't put a float into an int. We know that. But I really, really want to, for some reason that I can't explain. So I'm going to just print this out. It's not going to let me do anything with it at the moment because it's not going to run because I can't convert a float to an int. But I really want to. This is important to me. So what I can do is I can do what's known as casting. And what casting is me saying, yes, I understand that you can't turn a float into an int, or at least you can't guarantee me that the number I get as an int is going to be the same as a float. So what I can do is I can say, I understand that, I accept that, and I'm willing to take the risks. And I can put int inside some circular brackets like this. This is not the same as a function. I know it looks kind of, well, if it was a function, that both would be after the word, but in this case, the word is in circular brackets. I do apologize. In programming, you'll see similar symbols used for a lot of different things, and it's just one of those things that eventually you get used to. But if I have a data type, so it could be primitive or it could be a composite one, inside circular brackets like this is known as casting, like when you cast a line with a, when you're fishing. But basically, this is me accepting responsibility that I know that it cannot reliably convert a floating point into an int and they're going to be the same, but I want it to do it anyway. So the reason we have to, like, casting will allow us to do this, but the reason we have to cast is because we have to acknowledge that we understand the risks we take when we convert a floating point number into an integer. So our floating point number was 1.5. Does anyone want to hazard a guess for what the value of our int will be after we cast 1.5 into an int? Yep, any other guesses? So it's got to be a whole number. So theoretically, you would think it would be either 1.5, oh sorry, 1 or 2. Yeah, depending on how the casting works. Does it round down, or rounding down is effectively like deleting everything after the decimal point, or does it round up? Which, if I told you guys what is the closest number to 1.5, you'd say 2, because, you know, as humans we tend to round up. In this case, it gives us 1. So all it's doing when we cast from a float to an int, and if I change that to 1.9 to prove the point, it's still 1. It says, are you sure you want to do this? Yes, I'm casting it. I'm sure I want to do it. So it just says, okay, well, an int is just a float with everything after the decimal place deleted, so I'm just going to do that. So my advice for casting would be think very long and hard about what you're doing when you do it, and make sure that that is how it has to be done. Casting is the sort of thing which will produce horrendous bugs later on, because you're like, oh, it's 1.9, and then you cast it to an int and you do some stuff with it, and then you cast it back and suddenly the value is 1. And you're like, oh, you know, I had 1.9 in here before, I've got 1 in it, where is it? And it only becomes obvious way later that you've actually cast it to an int, and it's no longer what you would expect it to be anymore. So if you're ever in the point where you're like, I need to cast from a float to an int, or from one data type to another, ask yourself, is there another way I could be doing this? Sometimes there isn't, and that's fine, but oftentimes there probably is. And to make it worse, there's actually nothing stopping me from doing this. So here I have cast a float to an int and then stored its value in a float. And now that is going to give me, does anyone hazard a guess at what's going to print out? Take a stab. 1 point. 1.9. No. 1.0. Because it's cast it to an int, so it's turned it into 1, and then it's stored it back in a float, which is 1.0. So obviously this becomes quite confusing now, because I started with a float and I've ended with a float, but the values aren't the same because it's casted to an int at some point in time. So casting is definitely possible, and sometimes you'll have to use it, but I would just advise you guys to just be careful, think about, is there another way I can do this? We've actually dealt with comments as well. So no one's got anything at 12 that they need to get to? Okay, I might just try and finish this slide if we can and deal with arrays because we're not far. Okay, so I talked about how a string,
Sorry, I have one question where you do doubles and floats. In which case you will use doubles and in which case you will use...
Okay. Yep, so we can talk about that. So you'll notice in primitive, there is a few more that we haven't talked about. So int and long, so we've talked about int, we haven't talked about long, and we have float and double. So these two things sort of go hand in hand. Int and long are kind of similar, and double and float are kind of similar. So an integer stores a whole number. It can store a whole number up to the value of 2,147,438,647 positive to negative that same number. If I wanted to store a number which is larger than 2,147,483,647 plus or minus, I need to use a long. A long is exactly the same as an int, but it can store a number up to 9 followed by lots and lots of numbers. Yeah. So this is what an integer can hold. This is what a long integer can hold. Long integer because it's an integer which is really long. As far as what's actually going on behind the scenes, so if you remember we talked about we ask for an integer and it will give us a cubby hole, pigeonhole to put some memory in. For an integer, it will give us 32 bits to store our number in. So a bit can either be 1 or a 0, and then yeah, I'm not going to go into this at this point in time, but it's a size, so 32 bits. Your computer, so this computer has something like 8 gigabytes of memory. So we have 8 times 1024, which is 8,192 megabytes, which is 8,300,000 kilobytes, which is 8 billion bytes, which is 68 billion bits. So if I divide that entire thing by 32, I can store 2,147,000,000 integers until my computer will run out of memory. It's obviously quite a lot. With a long integer, or a long, they take up 64 bits. So I can store 1 billion of those before I'm going to run out of memory. So the question was, when do we use floats, when do we use doubles? It's exactly the same thing, actually, if we look at it. Floating point numbers can be as large as 3.40282,347 e plus 38. So what e plus 38, for those of you who aren't mathematicians, means is basically take that decimal place and move it. No, sorry, I'm telling a lie. Yeah, it's a little bit more confusing now. But they can store quite large and low numbers, but when you're talking about floats and doubles, we're talking about the precision that we can store in them. So an integer is quite easy to deal with because it's a floating point. Oh, sorry, it's a whole number. An integer can store 2 billion, up to 2 billion, and a long can score, that's million, billion, trillion, and I can't remember what the numbers are beyond that, but very big numbers. With floating points and doubles, it becomes a bit trickier because we actually need more space to store precision. So if I have a floating point of 0.1, that will take a certain amount of memory to store. If I have 0.01, that will take a little bit more memory to store. 0.001, 0.0001. And in fact, what I could do to make this even more obvious is let's change these. So adding an extra 1 after all of these doesn't really change its value very much. You have 10% 11%, 11.1%, 11.11%. You know, this is not a huge difference. It's not the difference between 1 and 10, for example. However, each time we add an extra digit to the end of this, we need a little bit more memory to store that digit. So where integers went from -2 billion to +2 billion, and longs went from, you know, some huge number to some huge number, when we talk about floats and doubles, sorry, we're more talking about what is the smallest possible number we can reliably, a fractional number we can reliably hold. So here we have floats are, because of the way they're represented in memory, they tend to get rounded a little bit. And it's saying here, according to processing, floats are not precise, so adding small values such as 0.0001 may not always increment precisely due to rounding errors. So if we're sort of getting down to needing to measure things at this level, double might be a better option, because that will allow us to do, does it give us an example? No, so it doesn't. But if you start adding numbers together and you start seeing weird rounding errors, so you'll have something like maybe 0.000001 plus 0.000001 might end up giving you something like 0.000003. And you're treating these as floating point numbers, you probably need to go to doubles. So that I don't have a firm answer for you, I'm afraid, on when to use one and when to use the other. It more comes down to how small or how precise do you need these numbers to be. The difference between, if the difference between this being off by, you know, 0.000001 is not a big deal, you know, a floating point is probably fine. Probably most of the stuff that you'll be doing in your MHIT, unless you're trying to land a ship on the moon or something, floating point will probably be fine. But when you're talking about things like measuring the distance between planets, this could be the distance of, you know, landing a rocket on it versus smashing it into the side of it. So,
for precision, we will use double.
Yeah, if in doubt, use double. Yeah. Again, the difference is that a floating point is stored in 32 bits and a double is stored in 64. So you can only store 1 billion versus 1.23 billion or whatever doubles versus floating points. Where I say you can have 1 billion doubles or 2 billion floats. So yeah, if you're dealing with something where it's really important that you have fractional numbers and they're very precise, use doubles. Otherwise, floats are probably fine for most of us. Likewise, if you're dealing with numbers which are larger than 2 billion, use longs. Otherwise, integers will be fine. After that little aside, I think we'll come back to arrays on Thursday. Does anyone have any questions at this point in time? No? Cool. And if you guys want to bring your laptops on Thursday, you're welcome to join along. I think we got, basically after this slide, 2 more really low-level programming things, and then we're going to get into actual useful, you know, drawing pretty pictures and stuff. Cool.
It's really similar to C#,
So, yeah, so we had C, and then object-oriented programming became popular. So C# sort of jammed object-oriented programming down C's throat. I think is a fairly apt sort of description, because a lot of people feel like the implementation was really poor. Then Java came out, which sort of did it with object-oriented. So Java was sort of more inspired by a programming language called Smalltalk, which in turn was inspired by a programming language called Eiffel, which was object-oriented from the start. So Java came in and was built around, and we'll talk about object-oriented programming. And then C# was basically Microsoft's attempt at throwing away C++, taking C and making it more like Java. So it's a very incestuous relationship between all these programming languages and stuff. So yeah, if you can do C#, if you can do Java, you can understand 80% of C# and vice versa, which is why we're doing processing, because Unity uses C#. So, but you know, there's still more of a learning curve for Unity than there is for processing. So processing, hopefully you guys will learn it, get comfortable enough with programming, and then when we move into Unity, you can be like, okay, the parts I don't understand, I can just kind of ignore, but the parts I do understand, I can start working with. Rather than sort of throwing you in the deep end, you just having the same thing that computer scientist students here used to have of, what does public static void main mean? All I want to do is print a number, but I need to write out this thing, and it needs to be written perfectly or the program won't compile. So yeah, it's like Java and processing is very similar to C#. Again, I got kind of distracted on that, but